researchers, as you know, ribosomes are very important structures for the bacteria because they are the factory of protein synthesis. Here, we see the translation of messenger RNA into proteins. So, if there is no translation in the bacteria, it means there is no protein synthesis, and it means at the end there will be no growth. Generally, most of, not all, but most of the antibiotics which shows effects on ribosome, on protein synthesis, they are generally act as bacteriostatic, but not all of them, most of them. The selectivity is partly because, as you know, the ribosomes of prokaryotic cells and eukaryotic cells are different from each other. Therefore, yes, there are some we see selective activity, but of course, some of the antibiotics which affects on ribosomes also affects on the ribosomes of mitochondria of human beings. So partly we can say they have selective activity. In this slide, you see the antibiotics which acts on protein synthesis, which inhibits protein synthesis, tetracyclines, aminoglycosides, macrolides or ketolides, chloramphenicol, lincosamides, streptogramins, and oxalidones. Of course, we divide the antibiotics, which shows effect on ribosomes, into two subgroups. Some of them acts on 30S ribosome subunits, and some of the antibiotics acts on 50S subunit of ribosome. The ones that shows effect on 30S ribosome subunits are tetracyclines, tigacycline, and aminoglycosides. Let's begin with tetracycline. Tetracycline, as I said, they show effect on 30S subunits. They enter the bacteria by passive diffusion or active transport. They show activity against many different gram-positive bacteria, gram-negative bacteria, Rickettsia, Chlamydia, and Mycoplasma. How they show their action? What is the mode of action of tetracycline? Tetracycline, as I said, they bind to 30S subunit of ribosome reversibly, and they inhibit the binding of amino acid tRNA, transfer RNA, to the acceptor site of ribosome. They inhibit the binding of amino acid tRNA to the acceptor part of which is found on ribosome. The second group of antibiotics which acts on 30S subunit are called as aminoglycosides. All the aminoglycosides are protein synthesis inhibitors. They are not static drugs. They are cidal drugs. Aminoglycosides act bactericidal, shows bactericidal effect. Okay. So how they show their action? Aminoglycosides change the shape of 30S subunit of ribosome. Therefore, because of the changing, we see because of the changes in configuration of ribosome, at the end, this change leads to misreading of codons of messenger RNA. If the codons of messenger RNA reads falsely, therefore there will be proteins which shows no functions. Okay, so it is very important. Sorry, I forgot to say, I said that there are three antibiotics which acts on 30S subunits. There are aminoglycosides, sorry, aminoglycosides, tetracyclines, and tigacycline. Three of them acts on 30S subunits. Tigacycline acts similar to tetracycline. It affects on it inhibits the binding of amino acid tRNA to the acceptor site found on the ribosome. Okay, now let's discuss the antibiotics which binds to 50S ribosome subunits. What are they? They are chloramphenicol, macrolides, lincosamides, streptogramins, and oxazolidones. The first one will be chloramphenicol. Chloramphenicol binds to the peptidyl transferase enzyme, which makes peptide bond between the amino acids. They inhibit the enzyme activity, so therefore it inhibits the formation of polypeptide bond. The second group is macrolides. Macrolides are also show static activity. They have a macrocyclic lactone rings. They are big molecules. As they are big, they cannot act on most of the gram-negative bacteria. They mostly act on gram-positive bacteria because as they are big, they cannot enter from the cell wall of the gram-negative bacteria. The prototype is erythromycin. Clarithromycin and azithromycins are the semisynthetic derivatives of erythromycin. How they act? As I said, they bind to 50S ribosomal RNA, and after they bind to the RNA, the binding site is found on the exit tunnel. As they bind to exit tunnel, the antibiotics, they inhibit the translocation of the messenger RNA. As they inhibit the translocation of messenger RNA, at the end, they prevent elongation of peptide chain. It's the same. Catolites act similarly as macrolides. They are also bacteriostatic. Then what is the difference between catolites and macrolides? Catolites bind to ribosomal RNA by two binds. However, macrolides bind only to domain 5. Catolites bind to domain 2 and domain 5. That means that catolites bind to 50S by two different targets. However, macrolides bind to ribosome only by one target. Therefore, catolites are more effective than macrolides. Lincosamides act similarly like macrolides. They are again binding to the site which is found on exit tunnel. As they bind to exit tunnel, then the movement of the peptide chain will be inhibited. At the end, we see inhibition of elongation of peptide chain. Streptogramins are another group which bind to 50S ribosomal subunit. There is a little difference between streptogramins and with the other antibiotics which bind to 50S ribosomes. Streptogramins, one by one, they are acting bacteriostatically. However, when we use two streptogramin together, streptogramin A and streptogramin B, all together, two of them together acts at the end bactericidally. They bind to the 50S ribosome irreversibly, and how they act, as I said that when we give streptogramin A and streptogramin B together, the One of them, streptogramin A, will inhibits the prevents the protein synthesis at the beginning. However, streptogramin B inhibits protein synthesis lately. Therefore, all together, A and B together, acts on the bacteria. The activity we see with streptogramins will be bactericidal. Oxazolidons, they are new antibiotics actually. They again binds to 50S ribosome. They inhibit the formation of 70S initiation complex. As they stop inhibits the formation of initiation complex, therefore they prevent the protein synthesis of the bacteria. This is a short explanation for activation of the linezolid oxazolidons. As they bind to the 50S part of the ribosome, they inhibit the formation of 70S initiation complex. Therefore, at the end, they inhibit the protein synthesis of the bacteria. This is a slide which shows summary of protein synthesis inhibitors together. Chloramphenicol inhibits the formation of peptide bond by binding to the enzyme. Macrolides, clindamycins, and streptogramins all together binds to the site which is found on exit tunnel. As they bind to the exit tunnel, they inhibits the translocation of messenger RNA. As they inhibit the translocation of messenger RNA, they prevent the elongation of peptide chain. Linezolid is a new antibiotic group. They binds again to 50S subunit. They prevent the formation of 70S initiation complex. And these are all together the antibiotics which acts on 50S ribosomal RNA. When we look at the antibiotics which acts on the 30S ribosome, tetracycline inhibits the binding of amino acid transfer RNA to ribosome, to acceptor part of the ribosome. And aminoglycosides again binds to 30S ribosome. They are cidal antibiotics. They make changes in the configuration of the ribosome. Therefore, this leads to the misreading of the codons of the messenger RNA. Just for making a little bit easier for the antibiotics, TAT means the antibiotics which binds to the 30S antibiotic, 30S ribosomal subunit, aminoglycoside, tetracycline, and tigecycline. However, the antibiotics which binds to 50S are cells, which means chloramphenicol, erythromycin or macrolides, lincosamide, linezolid, and streptogramins. Okay. Now we came to the inhibitors of the third group, inhibitors of nucleic acid synthesis. When we deal with nucleic acid synthesis, we see two groups. One of them are DNA synthesis, inhibitors of DNA synthesis. The other group is inhibitors of RNA synthesis. All of them, both the DNA synthesis inhibitors and RNA synthesis inhibitors, both of them shows bactericidal activity. At the first step, we will see the antibiotics which acts on DNA synthesis. These group of antibiotics are called as quinolones. Quinolones diffuse the peptidoglycan and cytoplasmic membrane very easily. Therefore, they act both on gram-positive and gram-negative bacteria. As I said, their activity, they show bactericidal activity. Their target is topoisomerase. What are these enzymes? As you remember from the bacteria genetics lesson from Dr. Shenar lecture, these enzymes, topoisomerase enzymes, especially 4 and 2, are very important enzymes for the bacteria. Why? At the stage of DNA replication, these topoisomerase 4 and 2 relaxes the supercoil of DNA molecules and initiates transient breakage. After a while, they again rejoins the phosphodiester bonds in the DNA. So they are very important at the stage of DNA replication, as you remember from the bacterial genetic lecture. The quinolones acts on these enzymes. If they inhibit these enzymes, this means that they inhibit the DNA replication. When they inhibit the DNA replication, there will be no DNA production, and at the end we see the death of the bacteria. The other group are the antibiotics which act on RNA synthesis. Here, the target is RNA polymerase. When the antibiotic inhibits the RNA polymerase, in that case, rifampicin is a very important antibiotic actually. Rifampicin inhibits the RNA polymerase. When you inhibit the RNA polymerase, RNA synthesis will be inhibited, and we see bactericidal activity. Mammalian RNA polymerase are different from bacterial RNA polymerase. Therefore, these antibiotics do not interact with human RNA polymerases. And the fourth group will be the inhibitors of membrane function. One of them is polymyxins. Polymyxins are very important antibiotic nowadays. Why? We are using them against, they are old antibiotics actually, but nowadays, as there are no novel, new antibiotics, we are using these polymyxins, especially colistin, against pan-drug resistant. Pan-drug means the bacteria is resistant all the antibiotics that we are using in the clinics. If we are using these antibiotics against pan-drug or multi-drug resistant bacteria in the hospital. How they act on the bacteria? They act on the bacteria by binding to phospholipids found on the outer membrane and cytoplasmic membrane. By binding to phospholipids of the membrane, they cause permeability difference, and at the end we see cell death of the bacteria. They are positively charged molecules, polymyxins I mean, and they bind easily to negatively charged cell membrane. They only act on gram-negative bacteria because they cannot pass the peptidoglycan layer of the gram-positive bacteria. The other antibiotic which acts on the cell membrane function is daptomycin. Daptomycin is only effective on gram-positive bacteria. They are also bactericidal. They cause depolarization of the cytoplasmic membrane. This is Ağrı Dağı. Ağrı Dağı, why I put a picture of Ağrı Dağı, a photo of Ağrı Dağı in this slide, because daptomycin is a product of Streptomyces rhosiosporus, which are isolated by scientists from the soil sample of Ağrı Dağı in Turkey. And the last group is the ones which acts as antimetabolic. I give only one example for this. Folate pathway inhibitors are one of the examples for antimetabolite antibiotics. They are acting bacteriostatically. Normally, human beings do not synthesize folic acid. We get the folic acid ready-made. However, bacteria had to synthesize folic acid in their body. So it's a good selected target for the scientists. So here, the antibiotic inhibits the enzymes which are necessary for the synthesis of folic acid. As they inhibits the enzymes, therefore the bacteria will not produce folic acid. However, folic acid is very important for bacteria because the bacteria uses folic acid, or the human beings are using folic acid for in many different pathways. So we finished the different groups of antibiotics. Shortly, we can say that the antibiotics which are affecting cell wall, uh, cell membrane, or nucleic acid synthesis acts, shows bactericidal activity. However, when we look at the antibiotics which inhibits folic acid synthesis or which inhibits protein synthesis, they are acting generally, they show bacteriostatic activity. Not all of them are, mostly they show bacteriostatic activity. Therefore, if you have a chance to choose an antibiotic, you have to choose the cidal antibiotics, in that case, cell wall inhibitors, nucleic acid synthesis inhibitors, or inhibitors of cytoplasmic membrane function. Okay. Uh, if you do not have a chance, if you have to choose a bacteriostatic antibiotic, of course you are going to use it. But if you have a chance, if you have a situation that you can use cidal antibiotics, choose the cidal antibiotics. Okay. Again, choose the antibiotic which have show selective activity. In that case, the beta-lactam group of antibiotics are good ones for selecting. Why? Because beta-lactam group of antibiotics are showing activity on cell wall of the bacteria, as we do not have cell wall on our cell on the human cells. Therefore, it is a very good choice for selecting against treating infectious diseases. Okay, now let's start discussing the antibiotic resistance and mechanisms of antibiotic resistance. Of course, many bacteria have ability to become resistant different kinds of antibiotics, and because of that, these resistant bacteria are now a great threat in our hospitals all over the world. So let's remember how the bacteria become resistant against antibiotics. One of the mechanisms is the bacteria can be instinctive resistance to the antibiotics that we are using. Or the second mechanism is they acquire resistance by using different kinds of transferring of resistant genes from one bacteria to another. Okay, interesting. Let's begin with intrinsic resistance. This means the bacteria have natural resistance against some of the antibiotics. It means that the bacteria transmits its to progeny vertically. So let's say that one of the A bacteria showing intrinsic resistance to B antibiotic. This means that the bacteria forming from the A bacteria will be resistant to B antibiotics forever. Okay, the mother and the daughter cells will be resistant to B antibiotics. For example, gram-negative bacteria intrinsically, most of them, not all of them, most of the gram-negative bacteria are intrinsically resistant to macrolides. Why? Because these antibiotics are so big, huge molecules. So these huge molecules cannot transfer from the cell wall of the gram-negative bacteria. As a result, they show intrinsic resistance against macrolides. We cannot use macrolides against these gram-negative bacteria. When we look at the acquired resistance, now some bacteria can become resistant to antibiotics by gaining resistant genes. How? They use three ways, as you learned from bacteria genetic lessons. One of them is conjugation, the other one is transformation, and the third one is transduction. By using three ways, by using conjugation, transformation, or transduction, the bacteria transfer resistant genes from one bacteria to another, and this is a very huge problem for all over the world, of course, in our country also. What are the mechanisms of antibiotic resistance? The first one is prevention of penetration of drug, or in other words, the antibiotic cannot enter the bacterial cell. The second mechanism is efflux of the drug. Drug enters the bacterial cells. However, the bacteria pumps the antibiotics to the outside, from inside to the outside, so it cannot show effect on bacterial cells. The third mechanism is alteration of the target site. Okay, when the target site changes, the antibiotic cannot go and bind to the target because target is changed. And the fourth one is inactivation of the antibiotic, or in other words, enzymatic destruction of drug. Let's see one by one all of these mechanisms shortly. First one is prevention of inhibition of penetration of the antibiotic. For gram-negative bacteria especially, the antibiotics can only generally enters the cell by using the outer membrane porins. Porins are very important for entering of the antibiotics to the gram-negative bacteria. If we see loss of these porins, or decrease in the number of the porins, or if there is a change in the structure of the porins, therefore the antibiotics cannot enter to the bacterial cell. At the end, what do we see? We see antibiotic resistance because antibiotic cannot enter the bacterial cell. The second mechanism is efflux of the drug. The antibiotic enters the cell. However, the bacteria uses pumps, efflux pumps, and get rid of the antibiotics. It pushes the antibiotics outside from inside. So, as a result, we see antibiotic resistance. In that case, I give an example. One of the bacteria, Staphylococcus aureus. It shows resistance against macrolides, lyncosamids, and streptogrammin B, all of them. There is a pump named MSRA. This pump pumps all these three antibiotics to the outside. Therefore, at the end, we see resistance against macrolides, lyncosamids, and also against streptogrammin B. The third way of getting resistant against antibiotic is changes in the target site. Again, I will give an example for a bacteria. In that case, we have a bacteria called as Staphylococcus aureus. In Staphylococcus aureus, we have penicillin binding protein 2. This enzyme, as I explained many times, makes transpeptidation in the cell wall, right? Beta-lactam group of antibiotics, all of them, penicillin, cephalosporins, or carbapenems. However, they came and they come and binds to penicillin binding protein 2, and they inhibit the transpeptidation. However, in some of these Staphylococcus aureus bacteria, they can produce a new target. They produce a penicillin binding protein 2A. This penicillin binding protein, which is called as 2A, cannot bind beta-lactam group of antibiotics. Therefore, it continues to make transpeptidation. As a result, we see resistance against beta-lactam group antibiotics. And the fourth way of producing resistance against antibiotics is enzymatic inactivation of antibiotics. For example, for aminoglycosides, there are many different kinds of enzymes which change the structure of the aminoglycosides. As these enzymes changing the structure of the aminoglycosides, at the end, the antibiotic cannot show any effect on the bacterial cell. Another example for enzymatic destruction will be beta-lactamase. What did we say before? We said that beta-lactamase enzyme breaks down the beta-lactam ring of antibiotics. When we break down the beta-lactam ring, this means that beta-lactam group of antibiotics cannot show any activity. So, in the case of beta-lactam group of antibiotics, because we are using mostly beta-lactam group of antibiotics in hospitals, gram-positive bacteria and gram-negative bacteria are showing resistance by using different pathways. In gram-positive bacteria, when we look at the mechanism of beta-lactam antimicrobial resistance, first of all, what did we say? There can be change in penicillin binding protein, target change. The target is penicillin binding protein. The alteration of the penicillin binding proteins will be, at the end, lead to antibiotic resistance. The second one can be overproduction of penicillin binding protein. And the third one will be the production of beta-lactamases. If the bacteria produce beta-lactamases, it will break down the beta-lactam ring. Then at the end, we will see the inhibition of activity of beta-lactam group of antibiotics. In gram-negative bacteria, we see all of them that we see in gram-positive bacteria. All these mechanisms are also seen in gram-negative bacteria. Plus, there are two different kinds of mechanism. One of them is the increased number of the efflux pump, and at the end, the efflux pumps will pump the antibiotics to the outside, or we see decrease in the porine expiration to reduce the drug's uptake inside the cell. So, unfortunately, these resistant genes that we see in bacteria can be transferred to other bacteria by plasmids and transposons. So, they lead resistance passing from one bacteria to another. So, antibiotic resistance is actually a global problem, okay? Exists on all continents, and it affects both low-income countries and high-income countries, and it affects both strong and weak health systems. So it is a very, very important problem all over the world. Why we are seeing antibiotic resistance? Because we are using antibiotics both for human beings and animals. The farmers are using antibiotics in farms against animals. They also use for prophylaxis for the animals. So all of together are leading to antibiotic resistance in all countries. Of course, most of one of the most important factors for treating of antibiotic resistance in, especially in our country, is poor hygiene and sanitation. What do I mean? As we do not wash our hands before touching the patients, we are transferring the resistant bacteria to the patients which do not have any resistant bacteria. We are transferring from one patient to another patient by our hands the resistant bacteria, unfortunately. And again, approximately 2 decades, there are very few antibiotics that are developed. Okay, so we do not have new antibiotics, and we are the ones that we have nowadays. We have huge resistance against these old antibiotics, and we do not have new antibiotics for using patients. So, what is the meaning of this slide? What did we say? The first antibiotics, penicillin, is first started. We started to use the penicillin at the middle of the 1940s. Before 1940s, the investigators, the scientists are call it as dark age. Why? We do not have any antibiotics, and as we do not have any antibiotics, the bacterial infections cause death of many millions of people. After we found penicillin, of course, day by day, the investigators, the scientists discovered new antibiotics. So we call this time as golden age of antibiotics, because the scientists are day by day finding new antibiotics. We use many antibiotics. We can use many different kinds of antibiotics against many different kinds of infectious diseases. However, look at here, beginning from 2000, maybe before the 2000, we have no new antibiotics or very little new antibiotics. Beginning from the 2000, the scientists call this time as dark age. Why? Because we do not have new antibiotics, and the antibiotics that we are using against the bacteria are showing resistance. Most of the bacteria showing resistance against the antibiotics that we have today. Okay, so what they write here, Semmelweis method, because they mean that as we do not have antibiotics in this century, we have to wash our hands, which Dr. Semmelweis recommended in at the middle of the 18th century, okay, 19th century. Okay, so as if you wash your hands, you stop the transferring the resistant bacteria from one patient to another. So wash your hands, and wash your hands. Okay, so healthcare workers, doctors, nurses. Doctors are worse than actual nurses, especially the men doctors. Women doctors are better than the men. Healthcare workers, nurses, technicians, or doctors all have to wash their hands, bind the woman, the girls have to bind their hair, do not have beard, please, and do not have nails, and please wear long white coats in the hospital. You must wear your long white coats in the hospital. So by this way, only you can stop transferring of multi-drug or pan-drug resistant. Pan-drug means bütün ilaçlara dirençli. Pan-drug resistant bacteria means you cannot use any of the antibiotics against these bacteria. So it is very big problem in our hospitals in Turkey. So this is a central catheter. This is a blood catheter. Actually, we are replacing this central catheter especially in cancer patients. Why we are putting this catheter, blood central catheter to the patients? Because we use this catheter for giving drugs to the patients because their vessels are very bad. And again, we are using this central catheter for collecting the blood samples for biochemical examination or microbiological examination of the patient. If you do not wash your hands and handle this central catheter, you will infect this central catheter and you will transfer the bacteria to the blood of the patient, and the patient will die at the end. If you collect the blood from the vessel of the patient, again, first you have to wash your hands before you touch the patient, before you collect the blood from the patient. What is this? This is the cell phone of the doctors or the nurses. And these are the bacterial colonies. As you cannot wash your cell phone, please do not touch your cell phone at the hospital before you wash your hands. There are many different publications which are showing that cell phones are carrying multi-drug or pan-drug bacteria in the hospital. As you cannot wash your cell phones, because if you wash your cell phones, you will destroy, of course, your cell phones. So therefore, please do not touch your cell phones with your dirty hands. Wear long white coats. If you are going to wear scrubs, as like here, again you have to wear long white coat on these scrubs. So these are the photos that I took last year in our hospital, in the streets when I was in the car. As you see, the doctors, nurses of our hospital are wearing their scrubs and traveling in the society with their self. You mustn't use your scrubs outside the hospital. Yes, these are the doctors and nurses going to home with their scrubs, which is very dangerous for antibiotic resistance. Okay. The lecture is finished. If you have any question, I can get your questions. I think we can get 2 questions.